Okay. Okay. So let's take our discussions further. Now, with the basic ideas about the thermodynamic systems and parameters and the dependence of fundamental parameters like pressure, temperature, uh, volume, specific heat, entropy, and the slightly higher level parameter, which are a series of parameters including energy, including internal energy, Gibbs energy, enthalpy, and Helmholtz energy. Let's see how we can apply some of these principles to studying phase behavior in a material. Okay, so to begin with, we will consider for a couple of classes phase equilibrium in a single component system, right? So I'll give you a formal definition of that. What will be called phase, and what are components, and what are degrees of freedom in subsequent classes. The objective now is actually to observe what is it that is equilibrium as it is influenced by some of the thermodynamic parameters, and in specific Gibbs energy or Gibbs free energy, how it influences that. And of course, we'll see how Gibbs energy changes with temperature, how Gibbs energy changes with pressure, and how it is influenced by a combination of things. And leading to that, we'll add further things to that. We'll construct a single component system or its equilibrium diagram for one single component system. And going forward, we can have multi-component systems. So, you know, again, to go back to our earliest discussions as to how or why a process happens. Process happens because it's not in equilibrium, right? If it is in equilibrium, there's no process as such. Now, something which is not in equilibrium has some imbalance somewhere, right? And I've said to you many times that that imbalance is actually related to an intensive property of a system, invariably. Okay, it is one type or the other kind of intensive properties which is not equal throughout the system. Okay, there exists a gradient of some of these intensive properties, right, which is sort of leading the system into some kind of a process. That's why it moves. That's why it is not stable. Right? That's why it's not static. Okay? The moment some of those intensive properties are static, meaning that it's uniform throughout the system, then the system would be in equilibrium, right? And you can have many such intensive properties. The most important ones are pressure, temperature, and Gibbs energy of various species. The other day I was giving an example of the price of a fruit, a particular type of fruit in a fruit basket. Okay. As long as all the prices of the fruits are not constant, so bringing one type of fruit and getting another fruit out of the basket is going to influence its total value or the average value. Okay, as long as that's not constant throughout the system. Likewise, when you talk about a material system, there are material systems like component A, component B, all sorts of things are there. And as long as the free energy of those systems, those individual phases are not uniform throughout the system, there'll always be some kind of a chemical movement. So, saying that there's a difference in this intensive properties means that there is some kind of a gradient, that there exists a gradient in the thermodynamic potential, and could be a temperature gradient, could be a pressure gradient, and could be a chemical potential gradient. And these properties, the gradient in these properties, they affect their respective conjugate coordinates, the conjugate thermodynamic quantities they affect. Like for example, what is the conjugate quantity of temperature? Okay, that's got to be entropy. So a variation in temperature is going to affect the entropy. Likewise, variation in a pressure or intensive, the gradient of pressure, that's going to affect volume. It will lead to either expansion or contraction, things like that. And eventually it will give you the PV kind of work. Okay. And that's what the basis of the process is. Likewise, if there is a potential gradient in the chemical potential or the molar free energy of the system, then that will lead to mass movement here and across. So the gradient in these intensive properties, they sort of affect the respective conjugate thermodynamic parameters. Now, when we talk about a single component system, then we are not talking about chemical potential gradient of various different phases. All right, we are talking about free energy of in the same chemical species, but of course in different phases of it. And then if we neglect that, then what are the other parameters that we have that can influence the stability of the system? And those are pressure and temperature. So I'm sort of bringing it to the bare minimum, requirements, in that henceforth for the remainder of this unit, we'll talk about single component systems, where we'll not talk about the chemicals, different kinds of chemical species. We'll try to see what the changes in thermodynamic parameters like pressure and temperature, most important ones, how do they influence the behavior or the stability of a single component system among its various phases, right? So, for example, a chemically distinct component would be H2O. Okay, that's water, and in water system you can have very many different kinds of phases. For example, you can have solid water, that is ice, and you can have liquid water, and then you can also have steam. So the idea that we're trying to build upon is what are the different variations in pressure and temperature that can give me the coordinates of stability of either water or ice or steam. Okay. Can I map the the coordinates of pressure and temperature onto something on diagram that I know, like this combination of pressure and temperature is going to give me this phase. That is typically what is called a phase diagram. Okay, and here it is phase diagram in a single component system. Anyway, so before we get to that, we need to understand the basics again as to how we can construct some of these diagrams. Now, you can have these diagrams mapped when you individually figure out the equilibriums between two contiguous phases, right? Now, if you begin with the discussion of talking the equilibrium between, let's say, H2O solid and H2O liquid, okay, let's say they are in equilibrium, and it's possible, that we have it 1 atmosphere, let's say, and 273 Kelvin, that's 0 degrees Celsius, and this is where solid water and liquid water can be in equilibrium. Okay. Now, when they are in equilibrium, how do we express that in thermodynamics? Is that the delta G, the change in molar free energy, is going to be 0. That is, let's say if you're talking about a solid to liquid transition, then the delta G would be defined as the free energy of water in the liquid state minus the free energy of water in the solid state. That's del G, and that is equal to 0, because they are in equilibrium. There's no process. There's no component disappearing and another phase appearing. All right. So that would mean that the molar free energy of water and molar free energy of ice, they are same. All right, and this of course refers to the molar free energy of solid and liquid water. Okay. Now, if you want to take a gross estimation of what the total free energy is, you can write G prime is equal to the number of moles of solid water multiplied by the molar free energy of solid water plus the number of moles of liquid water multiplied by the molar free energy of liquid water. Like, how do you calculate the value or the price of the fruit basket of different units of fruits and different kinds of fruits, right? So this is just an indication as to how you can calculate the total energy. Now consider a situation where you keep the pressure the same, keep the pressure at 1 atmosphere, but take the temperature to higher temperatures. For example, if you take the temperature more than 273 Kelvin, and then what's going to happen is that you talk about the same delta G, the change in free energy, that is the free energy of water in the liquid state, minus the free energy of water in the solid state. That's free energy of ice, and that is less than zero. That would mean that the molar free energy of water in the liquid state is less than the molar free energy of water in the solid state. What does it mean actually? If you have to define in words, the meaning of that is the escaping tendency of water from the solid phase is greater than the escaping tendency of water from the liquid phase. Right? That means water would like to be in the liquid state than in the solid state. Water is more comfortable being in the liquid state than in the solid state when the temperature is more than 273 Kelvin. Right? And the whole thing reverses when you take the temperature lower than 273 Kelvin. Let's not talk about T is equal to 273 Kelvin. That's an equilibrium temperature. Any temperature less than that means it is sub-zero temperature in our normal practice when we say that. That's delta G now is the same thing, but it happens that the molar free energy of water in the solid state minus the molar free energy of water in the liquid state is less than zero. Now that implies the molar free energy of solid water is lower than the molar free energy of liquid water. And that means the escaping tendency of water from the liquid phase is higher than the escaping tendency of water in the solid state. That means water likes to be in the solid state at a temperature less than 273 Kelvin. That's why we say that water is stable in the solid state at a temperature less than 273 Kelvin when the pressure is 1 atmosphere. I think it's very easy to understand for you because you know what's the natural thing for water to be when the temperature is lower. And like this, and this is where it is, where in the T is more than 273 Kelvin, and water would like to be in the liquid state than in the solid state. So it's eventually the molar free energy of those phases, one of those phases, okay, which at its minimum, prefers to be in that kind of a phase. If the molar free energy we're talking about of one single component among its various phases, the molar free energy in the phase at the particular temperature and pressure, if it is minimum, the material would like to be in that kind of a phase. That's the final thing we take from it. But then how do we achieve? How do we arrive here? It's a combination of things. So okay, just a little bit of a digression. So this is how we represent the Gibbs free energy or Gibbs energy in the pressure, temperature, or free energy temperature diagram. So we are now looking at the change of molar free energy with temperature of two different phases, of liquid phase and the solid phase. And here we are not changing the pressure. We are keeping it a constant pressure system, and say this is 1 atmosphere. And what is happening here? So you have this appears like a very straight line, but then it could be slightly curved. It's just a scale, and it can be really long curve. So it might appear that it's a straight line. Yeah, I've just drawn this, just to make it simpler, but it's not exactly a straight line. So let's say that the molar free energy variation with temperature is going like this for the liquid, and this for the solid state. Okay. Now let's get some of our basic things correct. If we can test it whether our diagram is correct or not. If you go back to the formula of delta G and how it's related to entropy, temperature, and pressure and volume, and you'll find that dG is what? This is VdP minus SdT, right? This is VdP minus SdT. If you go back to your notes, you'll see that. That means that when you keep uh, trying to see the variation of free energy or Gibbs energy in a constant pressure system, constant pressure situation, it simply becomes dG is 0 minus SdT. Right? Now you take a partial of the free energy with temperature at constant pressure, that gives you minus S, minus entropy. Okay. Now you want to see that mathematical expression here in this curve. You can pick any of the curves that for the variation of molar the free energy or Gibbs energy of liquid water with temperature or solid water with temperature. Doesn't matter. If you can take individually one, you'll see that this formula should apply here. And how does it apply here? We just need to see, that entropy is negative of entropy. Entropy is always a positive quantity. So minus of entropy has to be a negative quantity. And in this diagram, what is this quantity? Partial of G by T. It's simply the slope, because this is where you're plotting G, and this is here you're plotting T. And when you kept the pressure constant here, del G by del T is essentially the slope of this curve here. Essentially the slope of the curve here. Okay. Now this is minus of a positive quantity, that means a negative quantity. So this slope has got to be a negative quantity. That's why the curve is like this. It's a negative slope. This would have been a positive slope. So that means the negative slope here means in the prima facie, in oral aspects, our curve is perfectly fine. Right? If you want to go a step further and you want to take the double derivative of this curve, then you'll find this del square G by del T square, the same at constant pressure. That is again, taking derivative of this one with temperature, which is what's giving you Cp by T, and Cp also being a positive quantity, a negative of that would give you a negative slope. All right. So here you can apply this formula to see the slope or the overall shape of the curve for either the liquid water or the solid water. Okay, and that's how they're varying. Now, if we would like to see what is happening for a change from solid to liquid transition when we do it for water, right? That you could see here. That see if we do a solid to liquid transition, what is happening is that instead of G, we're trying to plot delta G from S to liquid. If you're talking about a solid to liquid transition, we are subtracting the free energy of a liquid phase minus that of the solid phase. Here you could do the same thing. For this, and you want to plot that with temperature, the del G with temperature, that would mean that you'll have to find out the del G for each temperature here. For this temperature, for this temperature, this temperature, and across the temperature window here, you'll have to calculate the delta G for this process of solid to liquid transition. That would mean the G of liquid minus the G of solid, right? And you'd see that you'd feel this is a liquid thing minus the solid thing, which will give you some kind of positive delta G here, all right? And this is a point where it's like solving, you might have solved in 10 plus 2 two equations, two straight line equations or two curve equations, where you define each straight line or a curve with a function, and if they intersect, both the functions actually would be operating according to this, for this point both the function would be operating in this point. That would mean that whatever variation of liquid water with temperature has, whatever variation of G of solid water it has with temperature, all of those two rules would be applicable here. Essentially what we're trying to say is that G liquid and G solid are equal here. Now if you want to plot the delta G by delta G S to L curve, then you will find that this is actually referring to as G, which is 0. The free energy change here is 0. That would mean that this point at this temperature, the solid water and liquid water are in equilibrium, right? So eventually what is happening is that if you deduct this one minus this, that's a positive quantity. This minus this, that's a slightly less positive quantity than this one. And this point minus this point, that's a little less, even lesser quantity than this point. And it comes to the point here, both the curves yield 0. But as you go to higher temperature, this minus this is a negative quantity. This minus this is a more negative quantity. And this minus this is even more negative quantity up to the point of here to here, which is largely negative. That's what is predicted here, that when instead of the molar free energy versus temperature, we are plotting here at constant pressure the change in molar free energy versus temperature, and the transition here we're considering is solid to liquid. Right? So for the solid to liquid transition, there is a temperature here, okay. Lower than that temperature, the solid to liquid transition delta G is positive. At temperature higher than this temperature, this equilibrium temperature, solid to liquid transition delta G is negative here. Okay, that would mean that at temperatures beyond this, the fact that delta G S to L is negative, liquid phase would be much more existent here. For temperatures beyond this one, temperatures lower than this one, delta G from solid to liquid has a positive molar free energy. Okay, that's one of the reasons that it will not be a stable transition. This transition will not happen. And that's the reason solid to liquid transition is not possible here. That means the solid has a higher free energy here. At temperatures beyond that, the liquid has a lower free energy and solid has a, I'm sorry, did I say it wrong? Yeah. Here at temperatures beyond this, the solid has a higher free energy and liquid has a lower free energy. Therefore, the liquid free energy minus solid free energy is a negative number. That's why liquid is going to be stable here. And that's the reverse part here. The solid has lower free energy here, liquid has higher free energy here. The free energy of liquid minus solid has a positive number here. That's why solid is going to be stable here, liquid is going to be stable here. Right? And you can simply see that in this, you can apply the same formula of del G by del T onto delta G. So delta G by del T is minus delta S. Okay, and again, this of course can be positive or negative depending on what is the delta S you're talking about. S is positive, delta S can be positive, can be negative depending on you're talking about solid to liquid transition or liquid to solid transition or anything of that sort. Okay. So we can actually write the simple equation that G is H minus Ts, and you can write the same formula for the solid phase as well as for the liquid phase. That is, Gs is Hs minus Ts solid and Gl is Hl minus Ts liquid. Now here, you got to be really careful about the transition. You're talking about a solid to liquid transition or the reverse. Okay, and depending on that, the signs and all the equations will change. Just an algebraic concept. Okay. So when we're talking about, we're trying to find out the change in free energy for a solid to liquid transition, then that would eventually come to delta H, change in enthalpy for a solid to liquid transition, minus T delta S solid to liquid transition. Right? Now, it comes to the point where two phases are in equilibrium. That is what this point is all about. Then here delta G is 0. Anything lower than that is negative, anything upper than that, higher than that is positive. And this corresponding temperature is the equilibrium temperature. And what do you call the equilibrium temperature between the solid phase and the liquid phase? You call it a freezing point or a melting point, right? And this is the temperature where these two units, these two parts are equal to each other. And that's the reason, delta G is equal. That is, delta H S to L transition is now equal to temperature times the entropy change in the same transition. Right? I think it's fairly clear. Now let's see how this delta G curve comes to the first place. That should be a combination of delta H, delta S, and T kind of things. Right? That's eventually which is giving you delta G, because immediately you cannot measure delta G. Free energy can only be measured by its components such as enthalpy and entropy, and that again would have to come from something like Cp, right? So from here only you'll be able to calculate free energy. How do we do that? Just take a look. So this is some of the numbers that I put here. Okay, this is how enthalpy varies with temperature. Right? Now, you know that delta H melting, that's a latent heat of melting of solid to liquid transition, and that's 6008 joules per mole at 0 degrees Celsius. Say we're talking about 1 atmosphere pressure. Okay, and these are the numbers given. The entropy of water in the liquid state at 298 Kelvin is 70.08. That's the same thing for given for the solid water at 298. And Cp and Cp of both H2O and the solid state and H2 and the liquid state are also given. Now, what we do is for the enthalpy term, we assign the most prevalent phase in 1 atmosphere and 298 Kelvin, and we assign that thing to 0. So here we are talking about what is 298? This is 273. Okay, this should be somewhere around 298. Okay, close to 300. Okay, so that at 300 at 298 Kelvin and 1 atmosphere, you'll see that what is the form of H2O that is stable, and you see it's liquid water, right? So we assign 298 Kelvin and liquid water to a value of enthalpy of 0. And any such reference to any other form or the enthalpy of liquid water at other temperature, we take reference from here. All right, and this is the curve of enthalpy of solid water and how it changes with temperature. And you see the subtle signs here is that the slope here and the slope here are different. That means the temperature of the influence temperature has on the enthalpy of water, liquid water, and the influence temperature has on the enthalpy of solid water are different, right? So there's kind of diverging. They are not parallel lines. So there's always the difference between these is not always the same. Okay, but there is only one reference point where the difference is going to be exactly the same, and that's here. Okay, that's a 273 Kelvin. That's the melting point or the freezing point of water, and that's where you can talk about the latent heat from here to here. That's the latent heat of water. This is going to be constant. But any other enthalpy change between other temperatures of these two different phases is not going to be exactly the same. And you can calculate that, of course. And how do you calculate that? For example, if we want to find out the enthalpy of water, liquid water, at any other temperature. So you simply do is you take the reference point 298, that's where you kept it 0. And from here, you pick any other temperature T. I want to see the enthalpy of water, liquid water at T temperature here. Then what I do is simply integrate Cp dt from 298 to T. Now this is what is written here. The enthalpy of liquid water at any temperature. This temperature can be not on the higher side. It can either be on the lower side. It doesn't really matter as long as you're integrating from the 298 point to T. Accordingly, it will give you a higher value, a lower value, depending on the temperatures, a higher temperature or a lower temperature. Okay. That's how you calculate the enthalpy of water at various other temperatures. How do you calculate the enthalpy of water in the solid state at any temperature? For that, you'll have to do some kind of a referencing, and that reference, as I said, is that 298 water liquid is 0, and from there you can calculate, you can come to any point here. That's what's written here in this equation. So let's say if I want to find out the enthalpy of solid water at this temperature, well, it's at 320 Kelvin, I want to find out what's the enthalpy of solid water. So what do? I see that I come from here from 298 to 273. I come on the liquid water curve from 298 to 273. How do I come that? I integrate liquid water curve from 298 to 273, which is what's written here. Cp of S. Oh no, this has got to be liquid. Sorry, there is a mistake here. It's got to be liquid here. Cp liquid dt. So we come from this line. We come from here, 298 Kelvin to 273 Kelvin, and then I come down on the latent heat of melting. Right? I take out the latent heat from here to here, which is minus this. So with this, I come from here to here, and then I add the heat from 273 to T, which is 320 degrees. Okay, so I add this one from here to here, and then integrate Cp dt, and that Cp is going to be the curve Cps. Right, which is what is written here. You might be worried about this negative sign here. That is actually should have been T to 273. Then the 273 to T. Oh, there's again a mistake. I suppose it's had to be. It's got to be plus here. Right, because here you are coming and then adding on to it. Okay, the signs will take care of themselves as long as you keep the limits the constant. The point I want to say is you want to calculate the enthalpy of solid water at this temperature. You take the reference from here and then you add and then add and then add. So this is how you would calculate these numbers. But the basic fact I wanted to bring here is that enthalpy curve changes with temperature. Enthalpy curve of any phase that you talk about, that changes with temperature. And when you talk about two different phases, the change can be slightly different. In that, you can only know at the melting temperature the enthalpic difference between these two phases, which is at the melting point. And the other temperatures you would not know because these lines are not parallel. All right. So you have to have the dependence of Cp curves of each of these phases to be able to find out exactly the difference between the enthalpies of the liquid phase and the solid phase at any other temperature. Okay, so from here we will see that the same thing exists for the entropies, right? And this is where I plotted the entropy of solid water and the entropy of liquid water. And you'll also know here that you can calculate the entropy change at 273 Kelvin between the solid water and the liquid water, because you know the delta H, that's the latent heat. You know the temperature, that's 273, and you should be able to find out the del S. All right. But that's at one temperature you know the entropic difference between these two. But in other temperatures you don't know. But there is a difference. There is a description of how Cp, DL, changes between these two temperatures, and based on that you should be able to calculate the entropy, the molar entropy of liquid water in across temperature with pressure being constant, and likewise the molar entropy of solid water across temperature and in its variation temperature. You should be able to find out. So what we have here is that the variation of enthalpy with temperature of these two phases and the variation of entropy of these two phases across temperature and both the systems when we have a constant pressure curve. Now, based on that, if you go back to the delta G curve or G curve, then what we have is a term called G is H minus Ts. Okay. Now, if we go back to this entropy curve here, this is entropy curve, but this is not an energy curve, right? You look at the unit here. The unit is joules per Kelvin, all right? And to be able to calculate the free energy, which is the effective energy of the process or the phase, then you need to be able to convert this one with the energy part, which is Ts. So with a rising temperature and also a rising entropy curve for both the phases, you should be able to calculate, and you must calculate, instead of S, you'll have to calculate the Ts curve of liquid water and the Ts curve for solid water, which is what we have done here. You'll see that this curve was steeper. Now this is a steep curve. This is steeper than this one. But then this is what the temperature line is, and this is S line. So when you do a calculation of Ts, then here the temperature is increasing, and you're multiplying this with this. That means you have a curve Ts which is going to be even steeper, which is what has happened here. Each of the curves of Ts are correspondingly steeper than their entropy curves. But now we are good here because this is the joules unit. This is the Ts line for liquid water, and this is the Ts line for solid water. Now what we have here is the Ts curve and the H curve. And then you should be able to calculate G is equal to H minus Ts. That is going to calculate that's going to give you the G curve. That's going to give you the G curve, and you compare the G curves of two systems, two phases, then you're going to get the del G curve, which is what we're doing here. All right. So, and if you look at this diagram, so class phone coach. Hello. So what we have here is from the S curves or both of the Ts curves, we find out T delta S curve for the solid and liquid transition, and for the two H curves we find out the del H curve for solid to liquid transition. Right. So how do you do this T del S curve? This T is constant. It keeps on multiplying with this. If you calculate the T del S, that is T into del S liquid minus del S solid, and you calculate that for every temperature and multiply that with temperature, which is what you're going to give you is this kind of curve. That is a T del S solid to liquid. And likewise, you can find out the del H curve, which is HL minus HS, and that's going to give you this kind of curve. Now, deducting one from the other gives you the del G curve. Okay, and which eventually what you got here is the del G curve, which is del G of S to L transition, which is exactly what we have seen in this curve. This is the del G S to L transition versus temperature. This is a sort of a pictorial or schematic that we've drawn, and this is the curve which is almost close to scale, and the numbers being printed on it here. This del G curve is actually a result of the calculation of S curve, H curve, the del H curve, and the del S curve, and the T del S curve. Combination of all of those things is eventually giving you the delta G curve. And this delta G S to L is what is talking about the solid to liquid transition and whether that is possible in a combination of temperatures or pressure. So what we have here is that if you go for any temperature less than 273 Kelvin, the delta G solid to liquid transition, that's going to be a positive number. That's why it is more than higher than the Z, than the zero line. So it's going to be positive. And since del G is positive, the solid to liquid transition is not favorable. That's not spontaneous, right? So in that sense, solid is going to be the most stable phase. And you know that at sub-zero temperatures, when you have ice, and ice is going to be the most stable one. Okay, and you go to any temperature in excess of 273 Kelvin, that's where del G for the solid to liquid transition is negative, and that's the reason the free energy of liquid is more stable, lower, and that's why the liquid phase is going to be more stable. So for the del G S2L transition, that's a negative number, and that would indicate that the solid to liquid transition of water temperatures more than 273 Kelvin, that's a spontaneous process, and liquid water is more stable. All right. So for the deliberation part, let's keep it here today, and we'll take it up in the next class from here onwards. And we'll take questions. We'll discuss some questions now. All right. So I'll stop the recording, and we will have some questions. If you have questions, please let me know.